Okay, look at this. An exam answer claims 150 plus 110 equals 4. You're looking at a standard 8-bit addition problem right here. On paper, the math actually looks completely fine, but the examiner gave this exact answer a big fat 0. So, why? Well, let me show you this massive, invisible trap hiding in this calculation so you don't make the exact same mistake yourself. Welcome to today's explainer for IGCSE Computer Science 0478, where we are going totally on the offensive. We are busting the biggest myths and mark scheme pitfalls out there. We aren't just memorizing textbook definitions today, no way. We are looking at exactly how you secure those high-level marks by understanding what Cambridge examiners are actually demanding from you. Now, what's really interesting about this is that to understand why that addition got a 0, we have to bring the math into the physical world. Notice this 8-bit register. It isn't just some abstract concept. It represents actual physical hardware. Inside a computer, a byte has exactly 8 physical slots, little transistors holding an electric charge. So when you add 150 and 110, you get 260. But here's the kicker. The highest value you can possibly store in a standard 8-bit register is 255. I like to call this the 9th-bit disaster. The mark scheme is incredibly strict here. You can't just write, the number is too big. To actually get the points, you have to explicitly state that an overflow error occurs because the calculation requires a 9th bit and there is simply no physical hardware slot to store it. That carry bit literally drops off into nowhere, making the entire calculation completely invalid. So remember, it's a hardware limitation, not just bad math. All right, let's transition from processing data to storing it. We all know file sizes matter, but how do we compress them safely? That brings us to run length encoding, or RLE for short. The absolute crucial point to remember here is that RLE is a lossless compression algorithm. It basically shrinks down a string of adjacent, repeating data items without throwing a single piece of the original data away. That means the uncompressed file can be perfectly reconstructed later. Pretty neat, right? Let's break this down step by step. Imagine you have a text file with a repeating string like 8 lowercase a's right in a row. Instead of saving A 8 separate times, RLE uses a clever little structure. First, it drops a flag, very often the number 255. This basically shouts to the computer, hey, a repeating sequence is coming up. Next, it stores the count, which is 08 for the number of repetitions. And finally, it stores the ASCII code of the character itself, which happens to be 97 for a lowercase a. So that whole long string just becomes 255, 08, 97. So why does this matter in the real world? Well, if you get an explain question on the exam, you need to use the exact right terminology. This lossless compression drastically reduces storage space requirements on your devices. And because the files are physically smaller, you get much faster upload and download speeds across networks. It also makes storing files on cloud servers way cheaper. But the absolute key takeaway? 0 data is lost when you reconstruct it, which is totally different from the lossy compression we use for things like JPEGs or MP3s. And this brilliantly illustrates our next common trap, hexadecimal conversion. When we look at this nibble matching table, it shows us that every single hex digit from 0 all the way to F maps perfectly to a 4-bit binary sequence. We call that a nibble. Now, computers love processing binary, but for us humans, reading long strings of 1s and 0s is tedious and super error-prone. That's why we use hexadecimal. It makes conversion incredibly fast. You just match the 4 bits directly to the hex character. But there's a massive trap hiding here. It's called the padding trap. Let's say the exam throws an awkward 13-bit sequence at you, just like this one. If you just start matching those bits from left to right, your entire answer is going to be wrong. You have to actively build the habit of adding leading zeros. We call this padding the binary sequence. You keep adding them until you have perfect sets of 4-bit nibbles. So in this specific case, you're turning those 13 bits into 16 bits by sticking 3 zeros right at the front. Only after you do that can you safely convert it over to hexadecimal. Okay, let's dive into this next one, because honestly, it catches out even the most experienced coders. I call it the pseudocode rounding myth. A lot of you are probably coding in Microsoft Visual Basic, Python, or Java during class. And in something like Visual Basic, you have these super handy built-in integer rounding functions, like math.round, which act as high-level shortcuts. The myth is that these exact same shortcuts automatically exist in standard IGCSE pseudocode. Well, I'm here to tell you, they definitely do not.
So here's the reality check for your exam. If you write math.round on your paper 2 algorithm test, you are going to lose marks. You simply cannot invent functions that don't actually exist in the syllabus pseudocode. What you have to do instead is manually script the logic flow. You literally have to write out the code that checks if the fractional part of a number is greater than or equal to 0.5, and if it is, then you manually add 1 to the integer value. You really have to bridge that gap between the comfortable coding environments you use in class and the pure raw logic required on the actual test.
Let's put this into practice and look at exactly how we secure those top marks. A standard, generic answer usually says something like, the binary number is too big for the computer. That gets 0 marks. I mean, it's safe, but it's way too shallow. Now check out the upgraded answer. The sum requires a 9th bit, causing overflow because the 8-bit register cannot store it. See the difference? This answer is anchored right in the scenario. It uses precise terminology, and most importantly, it proves to the examiner that you actually understand the underlying hardware.
All right, let's do a rapid-fire recap of today's non-negotiables. You need to lock these in for your exams. Number 1, always explicitly state hardware limitations when you're explaining binary overflow. Number 2, show every single step of the flag, count, and ASCII structure for those RLE calculations. Number 3, always pad awkward binary sequences with leading zeros before converting to hexadecimal. And number 4, do not invent non-existent pseudocode functions just because you're used to them in Visual Basic or Python.
So that covers data representation and algorithms, making sure they're actually understood, not just memorized. But here's a question to leave you with today. You now know exactly how data is stored, but do you know the exact sequence of events that happens inside the CPU matrix during the fetch-execute cycle? If this explainer made things click for you, make sure to subscribe to Ace the Exams. Jump right into our next explainer on memory architecture, and let's keep busting these exam myths together. See you there.